This question is dangerous because it is ranked to hard. This is a number 27 in the linear test, which is a paper version offered to students with accommodations. If you were to see this on a digital test, it'd be probably like a number 21 or number 22. Point is, it's a hard question. It's ranked hard. And it's hard not so much because the math is hard, as you'll see in a minute. It's relatively straightforward. There's just a lot of, well, first off, getting there is not necessarily easy, and there's a trap along the way that you might fall into, and that's probably what a lot of students would fall into. And the problem is it feels like it's right, and so we're happy and confident, and then we're blindsided when we get it wrong. So let's first talk about the mistake, and then we'll show you there's two ways to try to tackle this one. So the mistake is to say, look, these are similar prisms, so the sides are proportional to each other. In this case, the areas of these prisms are 58, surface areas 58 and 1,450. And we might say, look, I can find the multiplier. I can find the scale factor between these two prisms because I can see, look, if the area of one of them is 1450 and the area of the other is 58, if I divide the 1450 by the 58, I will find how many more times bigger is the large prism than the small. And when I put that in my calculator, I'll find 25. And so we might say, oh, so the prism Y is 25 times bigger than prism X. And so therefore, the thinking goes, I can apply that ratio, that multiplier to the volumes. So if the volume of the large one is 1,250 cubic centimeters, if I divide that by that scale factor of 25, I can sort of scale it down and say, okay, well, what's the volume of the smaller prism in that case, right? It's just 1,250 divided by that multiplier, which would get us, I think it's 50. Let me double check. Pretty sure it's 50. So 1,250 divided by 25. Yeah. So we'd say, oh, look, the volume of the small prism X is 50. So they want the sum of the volumes. So we'll add these together and we get 1,300. Seems very clean and very easy. And we put it down and unfortunately it would be wrong. So this is not, unfortunately, a way that works, even though it feels like it should. And the mistake was not this. This was fine and will be important later. It was this move immediately to applying that ratio to the volumes. So the problem is this ratio between the areas is essentially kind of a two-dimensional ratio, right? It's a ratio between a quantity in two dimensions, which is area. I can't just take that and apply it to a three-dimensional ratio. Nor could I say, for example, the sides of these prisms are in a ratio of 25 to 1, because that's a one-dimensional ratio. So I have to stick within the dimensions or convert appropriately. Like if I can use this ratio of 25 to 1 to find the other ratios, but I have to make some adjustments. So let me show you the longer way first, and then I'll give you the shortcut. So the longer way is to say, look, I've got these prisms here. We'll call this X and Y. And let's put in a length, a width, and a height for our smaller prism. And our larger prism, what we're going to do for the length and width and height was we're going to add a factor, a scale factor, K, for each of them, right? So we're taking the smaller prism and we're multiplying all of its sides by this scale factor K, by this multiplier K. And that's going to give us that K to 1 ratio between the sides that we're curious about. So fine. And now what we can do is say, look, what would be the surface area of this? What's the surface area of this guy? Well, the surface area would be the area of all the faces added up. So I've got 2 of these faces in the front, L times H. So I've got 2 L times H. And then I've got 2 of these faces in the side, 2 HW. And then I've got a face in the top and the face in the bottom, and that's 2 LW. For this guy, it'd be the same thing. I've just got these K's involved. So it would be 2 K squared LH plus 2 K squared HW plus 2 K squared LW. Okay. Now, what can I do? Well, I can factor a 2 out of these. So it's really 2 times LH plus HW plus LW. Here I can factor a 2K squared out of these. 2K squared LH plus HW plus LW. And notice what has emerged. The scale factor of the sides, which used to be K to 1, when applied in the case of the areas, is actually K squared to 1. right? Because that k-to-1 ratio that we came up with before was a one-dimensional ratio. When we apply this to 2 dimensions, when we find areas, we're essentially squaring that factor. So that is why it's k squared to 1. So that means if we were to compare these actual areas, which we did before, right? We did 1450 divided by 58. What happens? Well, let's see what would happen if I applied that here, right? If I said, okay, 2k squared times LH plus HW plus LW. Let's divide this by 2 LH plus HW plus LW, right? We're dividing the large area by the small area. Cancel, 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 cancel. Again, as expected, that factor of k squared pops out. So when I divided these numbers in the first move that I tried, and I got 25, that is the ratio of the areas, which is actually the square of the ratio of the sides in our prisms. So if k squared is 25, then k is 5. And now we are at the point where we can apply this to our volume, remembering that volume is going to be is a 3-dimensional ratio. So how does this work? Well, what would be the volume of these guys? So let me go to a different page here. The volume of the small one would be length, width, height. The volume of the large one would be k times length, k times width, k times height. Or the volume of this one is length, width, height. The volume of this one is k cubed length, width, height. And so here pops out the other idea that the ratio of the volumes is the cube of the ratio of the sides. Because again, we're scaling up that 1-dimensional scale factor to a 3-dimensional scale factor. And so we're just cubing it. So now we know that this is supposed to equal 1,250. And so we know as well that k is 5. And so when I plug these values in for my large prism, I'm able to find length times width times height, which is the original volume of the smaller guy. So 1250 is equal to 125 LWH. So LWH, which is the area or the volume of the small cube, is 10. So now that I have the volume of the small cube, which is 10, I add that to the volume of the small rectangular prism. I add it to the volume of the larger rectangular prism, and we get our answer, which is 1,260. So this approach I showed you was the formal way of doing this that kind of proves the shortcut that I'm going to show you in a second. You don't really need to do all this math once you understand the idea. The most important thing, though, is just to be very careful in questions involving ratios, involving similar figures, when you're moving between quantities of different dimensionality. In other words, from 1-dimensional values of like side lengths to 2-dimensional values of areas to 3-dimensional values of volumes. Be very careful just easily using one ratio for another. You have to make an adjustment for the dimensionality, for whether it's 1, 2, or 3 dimensions. So this process kind of formally shows you how this works and how that factor of k applies to the side lengths and therefore to the area as a ratio and therefore to the volume as a ratio as a squared or cubed version of that original value of k. But again, we don't need to do all of this work if we understand the idea. Like, let's go back here. We say, okay, look, the ratio of the areas is 25. The ratio of the areas, as we've seen from our work, is the square of the ratio of the sides. So if the ratio, we'll create a little table here. So we'll call this X and Y, and we'll call this the sides row and the area row and the volume row. We know the ratio of the volumes is 25 to 1, or the ratio of the areas is 25 to 1. We know the ratio of the areas is the square of the ratio of the sides. So what I can do is just square root this ratio to find that the ratio of the sides is in a 1 to 5 ratio, right? Because if I square root 25, I get 5, and the square root of 1 is 1. And so that tells me the ratio of the sides is 1 to 5. And now the ratio of the volumes is the cube of the ratio of the sides. So I can just go ahead and cube these values. So 1 cubed is still 1. 5 cubed is 125. And so now I know the ratio of the volumes is 125 to 1. And now I just go back to, instead of doing this was the mistake here, really. After all of that, the mistake was this move. Actually, we'll keep the 125 there. If I divided this by 125 instead, that is the ratio of the volumes. Out would come 10, and then I would have been fine. I could have plugged 10 in here, and then I would have gotten 1260. So this was the mistake in the what we'll call the naive way, right? The simplistic way, was dividing it by that ratio of 25-1. If I adjust that ratio accordingly to the fact that it is the square of the ratio of the sides and the ratio of the volumes is the cube of the ratio of the sides, I can still use that value and get an answer more quickly. So either way, we get 1260, whether you do it the long way or the short way, and that's the answer.